thing you have ever seen in space?
There's so many amazing things that we get to see up here. I don't think a day goes by where I don't poke my head down into cupola and look out the window at Earth and see something that is not just incredibly amazing or just blows my mind. It's new and it's exciting. Some of my favorite things to see up here lately has been the visiting vehicle traffic that we've had. So getting to see a free flying spacecraft in orbit approaching space station is just incredibly beautiful. And from a physics standpoint, just amazing and so impressive that this is something that, humans have built and figured out how to do. And, we're on board space station waiting for this vehicle to get here. It's very cool. And then on Earth, one of my favorite things to see lately has been the Himalayas at sunset. We've been flying over Central Asia at sunset pretty often. And then just beautiful beautiful islands in the ocean. Africa is always beautiful. There's always something new to see from up here.
Hi, my name is Liliana Briggs. My question is it hard to become an astronaut or someone who works at the space station?
Well, it does require a lot of work and a lot of training, especially to become an astronaut. But anyone who's willing to work hard, I think, can become an astronaut. The important thing is that you study science, engineering, medicine, or you have a background as a pilot. Typically, what most astronauts have prior to becoming an astronaut. Especially the science and engineering part is important because everything that we do up here on board the space station isn't somehow related to science and engineering. But the good thing is anyone who's willing to work hard, I think, can become an astronaut.
Maya Eka. My question is, which planet or space object is your favorite? An example, Jupiter, Saturn, a black hole, etc.
This one's easy for me. I've always loved Jupiter and Jupiter's moons since I was a little kid. And like I mentioned earlier, one thing scientists are really interested in the search for life in the solar system is oceans on other planets. And so some of my favorite planetary bodies are these places that we think have oceans, like Jupiter's moon Europa or Saturn's moon Enceladus.
Hi, my name is Jack. My question is, what features does your spacesuit have that allows you to breathe in space?
Well, there are several very, very important systems in the spacesuit. First of all, the oxygen tanks, which supply your spacesuit with oxygen that allow you to breathe. But at the same time, we also have to remove the carbon dioxide that we exhale. We inhale air, we use the oxygen, and when we exhale, we increase the amount of carbon dioxide in the atmosphere. And if we don't remove that, we could actually suffocate in our own CO2. And so, the system that removes the carbon dioxide from the air that we exhale is, in many ways, just as important as the systems, the oxygen tanks that supply us with oxygen for breathing.
Hi, my name is Joseph Wydeen. My question is, what are the pros and cons of being an astronaut?
Great question. I think there are a lot of pros. I don't know about cons. I guess, for the pros are easy. For me, I love exploration and the discovery that it brings and the adventure that it brings. I love being part of something that's so much bigger than myself, like the International Space Station program, that brings countries together doing something that's where we work for the benefit of humanity. So there's a lot of really great things about being an astronaut. I guess if you had to come up with some cons, I don't know. It could, if you don't like traveling, it's probably not the job for you.
Food, maybe.
Yeah, the food. Andy says the food, perhaps. Depends on who you are, but yeah, not too many cons for us.
Hi, my name is Dylan Delzell, and my question is, how many safety protocols or precautions do you take before going on a spacewalk to complete repairs or upgrades to the International Space Station?
A spacewalk is certainly one of the more riskier activities that we do on board the space station, and that's why it's one of the things we train for the most, including doing preparations on board the space stations prior to doing a spacewalk. And even on the day of the spacewalk itself, we have about 4 hours of activities to prepare us and to prepare our bodies before we even go outside. Because the atmosphere inside the spacesuit when we're out in the vacuum of space is so much lower than in here in the space station. It's about only about a third of the pressure in here. There's a risk of decompression sickness, a type of bends that you can also get if you dive. And so to reduce that risk, we have to breathe pure oxygen for a couple hours before we go outside in order to get rid of all of the nitrogen in our blood. And so there's a long protocol. It takes about 3 or 4 hours before we're even ready to open the hatch and go out on a spacewalk.
We would like to thank Mrs. Beth Foley, the Central Tree Middle School site.
The planet. Because of this, we are mounting the largest single campaign, the largest observing campaign for a single event in the history of astronomy. The good news is that it's going to do a spectacular demise into the atmosphere of Jupiter. The bad news is it's going to do it on the wrong side of Jupiter.
What Levy meant by the wrong side of Jupiter was that the fragments, which were estimated to range as much as a mile across, would be crashing into the backside of Jupiter as seen from Earth. And that meant that no telescope on Earth would be able to witness the actual impacts as they occurred.
Shoemaker Levy 9.
But on its way to Jupiter was JPL's Galileo spacecraft. By mere happenstance, Galileo would be in a position to witness the impacts live.
The Galileo spacecraft was en route to Jupiter, and that could look at the impact zone directly, whereas from Earth, all the impacts occurred on the backside, and they rotated into view.
About an hour after each impact, the crash sites would be viewable from Earth, allowing ground telescopes to witness the aftermath. The excitement in the astronomy community about such an extraordinary event quickly began generating extra sensational press.
However, I was at the supermarket last Thursday, in the line, and I picked up a copy of The Sun. It's one of these tabloids that you slip underneath your six-pack of Coke on the way out. And anyway, it says, comet crash will start U.S. ice age. No government agency will verify the impending day of doom, but sources say that's only because they want to prevent wide-scale panic and rioting. This is a report by Mr. William Rock. I understand there's a few members of the press here today, and if Mr. William Rock is among them, I'd like a word with him. After the talk, please.
But in the midst of Yeoman's witty remarks were actually some deadly serious implications.
The computer modelers are going nuts. There's a whole community of people within DOD who who do nothing but model the effects of an impact, a nuclear detonation on Earth or an asteroidal impact on Earth. The problem is they don't have any data. So what they would dearly love, of course, is a 100 million megaton impact on Earth to refine their computer calculations. There are some obvious problems with that. And so the same computer modelers are adjusting their code for Jupiter.
I have another question down here.
We only had about just over a year warning of this event. It raised an interesting question. What do you suppose is the minimum warning time we would have for any comparable event on the Earth?
That's something we have been thinking about. An asteroid that's likely to strike Earth is one that we probably already know about. And so if the orbit is well enough determined, we can simply integrate forward with the appropriate perturbations on the computer. The exception to that, of course, are the comets, the long period comets that can indeed come out of the sun, take us by surprise. But these apparitions of long period comets are far less frequent than the asteroids. But if a comet did come out of the sun, it would take us, it would pretty much take us by surprise, and there's not a great deal we could do about it, but that's a very low probability event.
Just as Chodos and Yeomans predicted, the first fragment of Shoemaker Levy 9 slammed into Jupiter's southern hemisphere on July 16, 1994.
Scientists didn't know what to expect because they were just little pinpoints with tails. And some were saying that these impacts would just kind of fizzle out, that we wouldn't even see anything. And then shortly after the predicted time for fragment A, we got a report that it was really there was a bright dot on the limb of Jupiter, so it was clearly visible, and we knew that fragment A was not one of the larger ones.
A massive fireball erupted, creating temperatures over 40,000 degrees Fahrenheit. The plume would rise nearly 2,000 miles above Jupiter's atmosphere. Over the next 6 days, at least 20 more fragments would slam into the giant planet.
As we went down the line, some of the bigger ones, when they impacted Jupiter, were releasing, by some accounts, millions of megatons of energy when they hit. Partly because they're coming in at high velocity, but also because these fragments were likely at least hundreds of meters in diameter each.
So in your mind's eye, sort of think of A as a 1 kilometer size object, maybe E is a 1.5, and then G, I suspect we're getting up to about 3 kilometers. What we're seeing is not deep in the atmosphere. While the projectile punches down deeply, all the hot stuff burps right back up to the surface. So these effects we're looking at are up on top of the normal atmosphere. They're above the ammonia cloud tops. All these wonderful features that we're seeing here is something that's been brought up from depth that's now deposited on top.
And one of these collisions with the G fragment, which was the largest one, generated an energy of something like 6 million megatons of TNT explosive, which is 600 times the global nuclear arsenal.
If you were going to ask what's the size crater this would make on the Earth, if we're right about our estimate of the size and the energy, if it hit a continent, it would make a 60 kilometer diameter crater, thereabouts. Material that's blown out of that crater would essentially blanket the Earth with a layer of fine debris that would just block sunlight. You'd just get dark all over the Earth.
It was not hard to imagine the repercussions of such an event aimed at the Earth. But there was not much of a response by NASA or the Defense Department to tackling the problem. That began to change 4 years later, after a prediction that an asteroid might hit the Earth in 2028 became front-page news.
That was a false prediction. And the scientist who made that prediction at the Minor Planet Center was basing it on really of approximations. We, on the other hand, could actually calculate the impact probability, and it was 0. No chance that this asteroid would hit the Earth. And so this became front page news in the New York Times and many other newspapers. Here we had one prediction that an asteroid could hit the Earth, and another group, Don and myself, saying, no, it can't hit. And so there was massive confusion, and I think this was a wake-up call for NASA.
By the time of this media frenzy, NASA was responding to a U.S. congressional directive to discover 90% of all near-Earth objects large enough and potentially close enough to cause global extinction of life on our planet. Today, it's estimated there are almost 1,000 of these large objects. About 90% of them have been located. But there are many more smaller but dangerous near-Earth objects. So far, nearly 5,000 of them have been detected and designated as foes, short for potentially hazardous objects. Most of the hunting for asteroids is done by ground-based telescopes. But determining their sizes and potential for causing damage is hampered by the dim light given off by these dark objects. But an infrared space telescope, originally called WISE, has been helping to fill this information gap.
This was a mission to survey the entire sky in 4 infrared wavelengths of light. So wavelengths longer than what our human eyes can see. And the objectives of the mission were pretty simple, to just make this incredible all-sky map with the goal of seeing everything in these different wavelengths. Well, it also turned out that this project was quite unexpectedly good at sensing asteroids. As it turns out, WISE was spectacularly effective at not just observing these objects, but actually discovering new ones.
After WISE's onboard coolant needed for stargazing was depleted, it was renamed NEOWISE and repurposed as an asteroid hunter. For an infrared telescope can do something light-seeking telescopes cannot do: determine the size of an object.
This is because we're measuring the heat that comes off of the body. So rather than sunlight bouncing off the surface, we're actually seeing sunlight that is absorbed by the asteroid and then re-radiated as heat. So you can imagine that if we can measure the distance to the asteroid, and we know its brightness in these infrared wavelengths, we can actually figure out how big it is, because that sort of falls out of the equations.
But the Space Telescope's second life is nearing an end. Now in development is a successor mission.
Now we're working on the Near-Earth Object Surveyor mission. This is a new NASA mission whose objective is really to go out and map out the entire population of near-Earth objects as completely as possible. In particular, we're focusing on objects that are large enough to cause what I would call severe regional damage, meaning they're 100 or 200 meters across, and that's equivalent to something that's about a 200 megaton nuclear explosion. That's pretty bad. From my standpoint, this is a fascinating problem for a few reasons. One, just fundamentally, it's a natural disaster that we can prevent through fairly straightforward means. We can literally go look up, and if we do a thorough enough job of it, we have a chance of actually predicting whether or not there is something that's headed our way. And even if the answer is no, it all coast looks clear, that's a really good answer. It means it's something we don't have to worry about. So that just nice, neat solvability from my perspective is a really wonderful and rare thing in science.
Comets usually aren't shy about making themselves known. But asteroids with their darker colorations are far harder to spot. Early visuals of them were made by ground-based antennas that use radar to create ghostly images like these. The first ever close-up visit to an asteroid occurred a year before the Shoemaker-Levy 9 collisions, when the Galileo spacecraft was able to take a slight detour to capture some bonus science. A NASA mission having as its sole purpose the exploration of asteroids was achieved by the Applied Physics Laboratory in Maryland. Their spacecraft, named near Shoemaker, flew by one asteroid, and then went into orbit around a second one called Eros. This was the first time a spacecraft had ever orbited an asteroid. After spending a year observing Eros, the team decided on a daring ending to the mission: to attempt soft landing on the asteroid, something never before done, and something the spacecraft was not designed to do. Pulling off such a feat required radar science measurements provided by JPL's Deep Space Network and the expertise of JPL navigators.
Right now, we've just completed doing the last set of navigation solutions. It's the last optical navigation update. And we provide that solution in case we want to adjust very slightly the time of the next set of maneuvers. And the group that has done the orbit determination for NEAR, both radiometric using the Doppler radio tracking, as well as the optical navigation using landmarks on the surface of Eros, are done here at the Jet Propulsion Laboratory.
Okay, we're starting the maneuver. Yeah, we're showing Doppler residuals are going down. Okay. Yeah, we're 1.7 from the landing site, Dave.
Yeah, well, let's see now
the slant range.
The maneuver started.
As navigators and as mission designers, this is the kind of challenge that we want. It's a very new, exciting, and challenging kind of mission to rendezvous with an asteroid and to attempt to touch it on the surface as lightly as we can. And I think we're certainly excited to find out what happens and how gently we can put it down.
In about 50 meters per second, or 50 meters below is what Gene says.
Those pictures are really spectacular. Yeah, you guys can celebrate now. It looks like we hit less than 2 meters per second, and it did survive enough to track on the surface now.
We have two-way lock.
We have two-way lock.
After surviving the landing, the spacecraft continued operating for another 2 weeks, an impressive ending to an already successful mission. The first spacecraft to fly by an asteroid and a comet was a JPL mission whose purpose was not to chase down near-Earth objects, but to test a dozen advanced but risky technologies that larger, more expensive missions were hesitant to use. This was an effort to show that future projects could be smaller, less expensive, and capable of flying at times autonomously. At the top of the list of innovations was ion propulsion, a technology pioneered by NASA's Gyan Research Center that years before had been proposed for a mission to Halley's Comet.
Ion propulsion is designed to give fast and flexible access to the solar system for missions of the future. The first time I heard about it was from a Star Trek episode. It was an episode called Spock's Brain, for those of you who are Trekkies. And to me, one of the neat things about working on a project like this is we're really getting to turn this fantasy into reality, and that's very exciting.
Mark Raymond, a self-professed space nerd, decided as a young child that he wanted to be a rocket scientist. And now he was living his dream, having been handed the reins to Deep Space One, a spacecraft that really did sound like science fiction. Ion thrusters make use of atoms of xenon gas, which are given an electric jolt. That disturbance results in an electric charge, and the ions shoot out of the engine at tremendously high speeds, upwards to 90,000 miles per hour. But because all of this is occurring on atomic scales, the thrust is incredibly gentle and slow. Going from 0 to 60 miles an hour will take Deep Space One 4 days.
The thrust from our thruster is comparable to what I feel from the weight of this single piece of paper in my hand. That's how hard the ion propulsion system pushes on the spacecraft. But with time, the thrust builds up, and ultimately we can achieve very, very high velocities. It's what I like to call acceleration with patience. spacecraft is also smart enough to know how hard the sun and planets are pulling on it, and it can actually determine where it's going. An analogy I like to give for how powerful the combination of autonomous navigation with ion propulsion is, compared to what we can do today, these two technologies are like having your car find its own way from Washington, D.C. to Los Angeles, arrive at a designated parking space, and do it all while getting 300 miles per gallon.
7, 6, green board. 5.
Of course, Deep Space One first had to get off the ground.
Main engine start and liftoff.
That called for a rocket having a conventional propulsion system.
The Delta rocket with Deep Space One, testing the spacecraft technologies of the next century.
Within minutes of the launch, Deep Space One's high-risk billing seemed already in play.
When we launch a spacecraft, we calculate where it will be in the sky and what time it will turn on its radio transmitter.
Go ahead. They're still running the receivers attempting to acquire the ascending screen at this time.
And the signal didn't show up. That's not where you want to run into problems on the mission.
Flight 8. Go ahead. Just reported again. They still do not see a downwind signal. I copy that. Thank you very much. We're going to ahead and proceed with our contingency plans here. Stand by.
There were a lot more issues on that spacecraft than other spacecraft I've flown since.
Go ahead. Just reported again. They still do not see a downwind signal.
A lot of things go into that because we're kind of pushing the boundaries. We're building these things for the first time.
Go ahead. Also be advised that the station is currently experiencing some receiver problems and they do not see a signal. I copy. Thank you. Waiting here.
This moment of flight jitters eventually passes when the spacecraft reports that it is alive and well. The team spends the next 2 weeks preparing for turning on the spacecraft's ion propulsion system for the first time.
This was the big day when we were actually going to light it, go to warp power, emit that cool blue beam, and get underway with our powered flight.
At 18:59:00.
Ace, this is flight. You are go for radiation of India Charlie 018, X-ray 01 at 18:59.
This is the moment that is hoped will change the future of deep space exploration.
Right, once accelerated, shifts down some. Real high frequency stuff. Advanced right, the shape and dots and stuff. You're almost dead on. That's right. Seconds. This will change to true. It will go through the startup sequence.
Yes, one team, this is mission director. Prepare for warp speed.
So we had all these people here. We sent the commands to the spacecraft, and sure enough, right on schedule, the spacecraft went through its own final procedures to start the engine, started the engine. It worked great.
There it goes. There it goes. All right.
Yeah, congratulations, Jack. Everybody. Yeah, congratulations. Not me. You guys.
Hey, Jay.
We lit off.
You're looking at it.
Right there. Jason.
There it is.
Everybody in mission control was all excited. People in the hallway were all excited.
Oh, we're in standby. We had 20 recycles.
We're seeing TDC mode.
Well, the spacecraft had thrust for 4.5 minutes and then stopped. And so we immediately started trying to diagnose the problem.
I think we need to focus on this. Roger that. Please consider your evaluation for restart.
Downlink data. Excess people filter themselves out of the room. A lot of noise, a lot of crowding.
After regrouping, the team tries restarting the engine.
Thank you, flight. This is mission director. You're authorized to radiate. Command
Command DSN 5 Uniform Charlie 065 Alpha 01. All units be advised the thruster is off again.
Time limit, and we shut down and we're now in standby.
Roger that. Is there an evaluation of what caused the sequence of events?
There's a discussion going on right now about that. We'll get back to it.
So every time it arcs, the high voltage cuts off and then goes back on automatically. Right, to try to clear the fault.
Right. That's good for
A number of attempts are made, all with the same result.
Shut down.
Did it happen right away as time goes?
Each time that happened, our spirits went down a little more. Ion propulsion was the primary objective, and here we were unable to get more than 4.5 minutes of thrust. And in fact, our minimum success criterion for Deep Space One was to thrust with the ion propulsion system for 200 hours. Well, we still had another 199 hours, 55 minutes, and 30 seconds to go.
While disappointing, these kinds of shutdowns didn't come as a total surprise. Similar events have occurred during lab tests.
Plasma wave is we're going to get the search close and see how they respond. While we're working, we're burning for a while. That's probably a noisy burn right there. Because it should clean up to be fairly clean once the accelerator works right.
There may have been just a small piece of contamination in the thruster, in the ion engine, left over perhaps from launch when the whole spacecraft was shaken violently.
Can you set up the times relative to what we're seeing?
We did a number of things, including turning the spacecraft so the engine would point toward the sun and away from the sun. That would loosen this particle so it could just drift away.
After 2 weeks of using the sun to alternatively heat up and cool down the spacecraft, the propulsion system was tried again. The era of ion propulsion had arrived.
Over the course of the mission, we put it through its paces, we tested it thoroughly, we showed we could count on it to propel the spacecraft, we could navigate with it. It was wonderful. That meant that many subsequent missions that it would have been impossible without ion propulsion then were possible.
What followed was a whirlwind of testing the other technologies on board. And only 9 months after launch, with almost all of the mission's objectives met, the team was eager to fly by an asteroid named Braille.
That was a great way to take all these new technologies and show that you could do planetary science. We're out there, let's go use all this fancy stuff to go take pictures of something.
The asteroid Braille was co-discovered just 6 years earlier. One of the two co-discoverers was Eleanor Glow Helen, a JPLer and a pioneer in asteroid hunting. That the asteroid was found was an impressive feat, for the asteroid was so dim that Deep Space One was almost unable to spot it. And just hours before the encounter, a software bug caused the spacecraft's computer system to overload, requiring a reboot.
The fact that the spacecraft was very temperamental, almost made us not able to do that encounter. We went into safe mode the morning we were supposed to do this flyby. I got a text message. Back then, we didn't have cell phones. We just had these pagers, but the pagers were fancy ones that you could get a text message on. I got this text message that said, "We're in safe mode," and I'm like, wait, the encounter is tonight. It takes 3 days to recover from safe mode. Oh my gosh, I better get into work.
Racing against the clock, the team beamed up new instructions. The last command was transmitted with only minutes to spare. The science results were modest. The few images of the asteroid were taken at a further distance than intended, causing them to appear out of focus. Still, this had been the smallest celestial body ever targeted by a spacecraft, coming within 17 miles. An impressive accomplishment that convinced NASA that the mission was worthy of a second shot. The next target would be a comet. But in November 1999 came the most serious crisis of the entire mission. The spacecraft's star tracker, which looks at stars to determine the spacecraft's orientation, ceased working. Without it, the spacecraft was left in a state of confusion, knowing neither up from down nor right from left.
The star tracker on Deep Space One is responsible for telling the spacecraft how it's oriented in the zero gravity of space. We know where it is and where it's going, but we can't tell where it's pointed without the star tracker.
The spacecraft, for all intents and purposes, could accomplish nothing of value without the star tracker. There was no reasonable, rational prospect of being able to continue the mission. But I didn't want to give up that easily.
Normalize all these to one number and decide what to add or subtract.
The team started working on ways that we could rescue this spacecraft from across the solar system. With a fatal, catastrophic failure for which there was not even a concept for how we might recover. All we had to work with was what was on board the spacecraft, plus, of course, ones and zeros that we could send to it.
VSS 45. VSS 45.
There followed months of very, very long hours, every day, constant stress, this feeling of, I want to get this spacecraft working again.
There ended up being only one possible fix: to send up new software that would reconfigure the spacecraft's camera to do double duty as a star tracker and a camera.
The science camera was not designed to do that and had a much narrower field of view. The star tracker has a giant wide field of view that can see a significant part of the sky. The science camera is sort of like trying to drive your car looking through a soda straw. Basically, what we needed to do from then on was pick a direction that we wanted to thrust, find a star near there, and then thrust at that star for a while. And then after a while, the navigators would tell us, now we need you to point the thrust in this other direction. Like, oh, okay, let's go find a star over there that we can thrust at.
Like a sailboat tacking with the wind, Deep Space One zigzagged its way to a comet named Borrelli. The closest approach would be on September 22nd, 2001. 11 days before then was 9/11, the day the United States was attacked by 4 hijacked planes.
It just turned the world upside down. Personal emotions about it was, by gosh, we are going to accomplish this thing. We aren't going to let this stop us. The lab is completely empty. There's guards everywhere with guns, there's guards with shotguns at the front gate. And, we have special permission to be the only people allowed on lab because we have this operations work to do. It was very emotional. Said a lot of people had their American flags. I'm a volunteer for the JPL search and rescue team. I had some inkling of what was going on in New York, so I wore my search and rescue helmet that day.
We had faced so many difficulties. We'd had to make so many decisions. And, Deep Space One had not been designed or built to encounter a comet. And the encounter at Borelli didn't go the way we expected. Instead, it was perfect. Years of nursing along this damaged, wounded spacecraft. It was pretty rewarding.
Scientists were elated with what were then the highest resolution pictures ever taken of a comet. The stubborn team of engineers could also take pride in having opened up a new chapter in robotic space exploration. Three months later, with the spacecraft running low on fuel and no other science destination within reach, the mission was officially declared over. Today, Deep Space One, a small spacecraft operated by a small team with big hearts, silently circles the sun.
Perfect, okay. See ya. We're not?
It is nice up here.
Correct, copy. You're clear to ground.
Okay. Here we go.
During the same year that Deep Space One flew by asteroid Grail, NASA's first mission devoted exclusively to comet exploration was underway. The vehicle wasn't a balloon, although this one was part of a critical pre-launch test. The main goal of this mission, called Stardust, is to send a spacecraft out to capture samples from a comet and then bring them back to Earth. What's been pushed out of the balloon is a model of the capsule that is to contain the comet particles. This drop test is to determine how hard a landing the capsule can withstand. The landing area is the Dugway Proving Grounds, a remote military facility in northwestern Utah. The winter weather makes for a cold outing, but the wet ground will hopefully make for a soft landing.
They landed right on the road.
Oh, great.
A comet sample return mission was first proposed for Comet Halley. The scientist involved in that original proposal, Don Brownlee, had never let go of the idea. And the comet that's been chosen to sample, Wilt 2, has an unusual history, as comets go.
We have this wonderful situation. The comet came from the edge of the solar system, came into the inner part of the solar system where we are, and then we sent a spacecraft out halfway to Jupiter to meet this thing. So it's really kind of a sort of a magical situation, I think.
Wilt 2 is believed to be as old as our solar system, and it is thought to contain some of the most pristine and pure materials out of which the solar system was formed. That made for a convincing case to greenlight the mission. And the price tag didn't hurt its selection chances either. This was one of NASA's early faster, better, cheaper missions. The goal was to fly a spacecraft for less money and on a faster schedule. And Stardust promised just that. The spacecraft is a straightforward design having few bells and whistles. It is to be powered by solar panels. But no spacecraft has ever been asked to travel as far from the sun using solar energy as this mission will have to go. And no spacecraft had ever flown as close to a comet as was planned for Stardust, which is why the spacecraft is front-loaded with bulletproof shielding.
We're playing a game here. We want to go close as possible to the comet to get the best images and to collect the most amount of sample. But we don't want to get hit by large enough particles to destroy the spacecraft.
Stardust's most unusual feature is its comet dust collector. It resembles a tennis racket full of ice cubes. But this blue material is an ultralight compound called aerogel. Sometimes referred to as frozen smoke, it's a solid that is 99% air. JPL researcher Peter Sue made a career out of finding ways to use this strange material.
Aerogel, although it's very fragile, but it has very high compressive strength. And let me demonstrate to you, this piece of aerogel weighs about 10 grams. This piece of plexiglass is about 50 grams. That's already 5 times the weight. This is 1,000 grams. This is another 1,000 grams, 2 kilograms. So this is 2,000 times its own weight.
While aerogel can carry more than its own weight, it is also porous enough to capture intact comet particles that are moving faster than a bullet. A year after its launch in 1999, Stardust gathered in the first 2 samples of interstellar dust. Then it was on to a full dress rehearsal of a comet encounter by flying by asteroid Anne Frank. To protect the spacecraft, Stardust was kept at a safe distance of over 2,000 miles. Still, engineers were delighted with the test. And scientists even got a far-off peek at the asteroid. Another year passes before the encounter with Wild 2. And as the day nears, the comet isn't cooperating. It's dimmer than expected. And that likely means there will be far fewer dust particles to collect than wanted.
As far as the brightness of the object, the photometry is concerned, we're somewhere between 5/7 and 5/10 the amount of dust that we expected to observe. There's less light coming from the thing this time, less flux.
The only way to collect more dust is to fly closer to the comet. But flying closer increases the risk that the mission could be lost.
Now, originally, these observations we weren't going to use to change our plans. We were just going to use to confirm that we're still in the ballpark.
This meeting offers a rare look into how such pressure decisions are made in real time. The encounter is only 3 days away. At the table are JPL engineers, navigators, scientists, a NASA headquarters representative, and by phone, the spacecraft contractor Lockheed Martin.
We have not tested it.
Given the concern that debris shedding off the comet might ruin the encounter or even destroy the spacecraft, the question on the table is how close should the flyby be?
I didn't make too much noise about going to 300 at the time.
because there is a chance that we might lose all of the images if we go into 150.
If we do go into 150, pretty much are close to collecting the particles, but if we go into that close, there's about a 4 times higher chance we will lose the image sequence during the flyby. So what's science assessment?
Well, my recommendation is we target for 250, which is a modest correction. This is better than sticking at our target value of 300 kilometers we did in the past. I'll use Sham's golf analogy. We're approaching the hole, and we're doing tweaks as we're coming in.
And there's still a probability it'll work. I mean, it's not saying that it won't work. It's just
what do you mean?
Yeah, but
what do you mean probability?
Well, I don't know. I mean, I'm not saying it's an absolute failure. I'm not saying it's an absolute success.
You know, if we're opening up, we're exposing ourselves to some new risk we haven't imagined, then that's really a stupid thing we'll always be crucified for. And if we lose imaging close in, we take a gamble. We've always known that the comet could disintegrate at any minute. It could turn off. It could turn on. It's an uncontrolled beast.
Okay, I think another data point is independent of science. I will not support a 150 kilometer flyby. I will be dead set against it.
So your recommendation is 250?
250.
After all this back and forth, the team is in accord. The trajectory will be changed to bring Stardust 50 kilometers closer to the comet. If Vilt 2 has any more last-minute surprises, there are preloaded contingency plans aboard Stardust that hopefully will allow the spacecraft to respond on its own.
Hey, Tony, you're really fading out and breaking up now.
Yeah, we got a lot of static here.
Good morning. This is Stardust Mission Control at NASA's Jet Propulsion Laboratory in Pasadena, California.
It is now one day after New Year's Day 2004. The time for the comet flyby has arrived.
After nearly 5 years and 2 billion miles of space travel, Stardust is about to perform a flyby of comet Vilt 2.
It is also just one day before the landing of JPL's Opportunity rover on Mars. A busier time would be hard to imagine.
all station start assistance. This is closest approach distance.
We are going into an unknown environment. No spacecraft has ever gone this close to a comet.
Is that consistent with the 4-degree roll, which we expected to see?
The moment of closest approach passes. Stardust is still sending back a signal. It has survived the encounter.
Life is tremendously good. We've flown through the worst of it, and we're still in contact with our spacecraft.
Soon the spacecraft will be transmitting back news that it has captured thousands of particles, and to the delight of everyone, images of the comet.
You seen these pictures? That's fantastic. Yeah. Nothing else in the universe looks like this, you know?
That's right.
Nothing.
Looks a lot different than Wally. It looks a lot different than Borelli.
We're expecting some kind of rubble pile looking thing, which is a dark black object, broken charcoal briquettes or something. It's just kind of a smooth, boring thing. We were completely wrong.
Vilt 2 was a far stranger object than imagined. The comet's surface was dotted with towering pinnacles, steep cliffs, and oddly shaped craters.
It was absolutely astounding. The first picture we got back showed these tremendous features, which we now call left foot and right foot, which looked like someone in a big clown suit just put their left foot and right foot into the surface of the comet. Yet these are kilometer-sized features that are hundreds of meters deep.
The flyby, though, had been far more dangerous than expected. Dozens Dozens of jets had bombarded the spacecraft at a rate of 1 million particles per second. Like a geyser erupting, jets are outbursts of material from a comet caused by heating by the sun.
We fly these missions, and we do the best job possible to model everything we think will happen. The closer you get, the more dust you get. Maybe there's a few big jets that are waiting for us, gunning for us. And our prediction was no. And we were proved wrong, quite wrong. But we did survive.
With its bounty of comet and interstellar particles safely on board, Stardust, sandblasted but still sturdy, began its 2-year journey back home. Once near the Earth, Stardust is to release its capsule, which will have to endure the intense heat of re-entry through the atmosphere. Next, a parachute is to deploy, which should provide the capsule with a soft landing in Utah. Helicopters are to retrieve the capsule. Then this cosmic cargo is to make its way to a lab at the Johnson Space Center in Houston for detailed examination. That's the plan. But a parachute had failed to open on another JPL mission called Genesis. Its capsule, containing samples of the solar wind, slammed into the Utah desert. Fortunately, enough particles survived the hard landing to be useful for scientists. But no one wants to see a repeat of such a shattering experience. After a journey of 7 years and nearly 3 billion miles, the capsule re-entered the atmosphere at a speed of nearly 29,000 miles per hour, the fastest re-entry of any human-made object on record. Witnessing the spectacular entry were scientists flying aboard a NASA Ames research plane.
17 degrees aft.
The blazing capsule, filled with comet particles, now looked to be itself a comet.
Okay, we have confirmation of a main chute.
All stations, main chute is open. We're coming down slowly.
Stardust was the first sample return mission since Apollo astronauts brought rocks from the moon back to Earth. Inside the capsule were thousands of samples of comet and stardust that were shared with scientists worldwide. These particles, the only known samples from the outer solar system, were once part of a primitive, ice-rich body that formed well beyond Pluto. But surprisingly, many of the rock dust particles were similar to those found in primitive meteorites that formed the sun. Apparently, the forming area lysine, a fundamental building block of life. Its detection has added credence to the idea that the materials necessary for life to arise may be spread in abundance across the universe. While Stardust brought back samples from a comet's surface, JPL's Deep Impact mission was designed to hit a comet in hopes of revealing what materials reside in its interior.
5, 4, 3, 2, 1. We have ignition and liftoff of a Delta II rocket carrying Deep Impact, NASA's journey to unlock the mystery of the solar system's origin.
And the air starts have ignited.
Being launched into space are actually two spacecraft, the Deep Impact Mothership and its cargo, a small washing machine-sized impactor to be released to collide with a comet. The two spacecraft were built by Ball Aerospace, with JPL responsible for management oversight and creating the especially complex software required for the mission.
We had 12 months to complete the assembly of the prime spacecraft, complete the assembly of the impactor spacecraft, go through the entire environmental test program, fix the flight software, fix the fall protection, fix all the bugs that we found along the way, and figure out in parallel how to hit the comet.
Hitting a comet was something no spacecraft had ever done. And to have any chance required creating computer simulations at JPL. As often as not, the early simulations resulted in misses. And then, 2 months before launch, a near catastrophic mistake was made.
There was that black day in November where somebody came in and accidentally deleted all the files. Sequences that we were working on for post-launch, encounter, everything. Gone on one night. Deleted because somebody thought they needed space on a server. And it was like, how in the hell do we ever recover from this?
The solution was to work intensely long hours. The pressure didn't let up post-launch. The journey to the comet, named Temple 1, was a short one, just 6 months. When only halfway there, the comet was already in sight. The JPL flight team barely had enough time to settle in before the encounter was upon them.
Normally it takes many months to launch a spacecraft and check it all out in flight and learn its idiosyncrasies and get it all calibrated and working good. And so to launch the spacecraft and only 6 months from then have an encounter was very challenging. We were sleeping in our offices level of working hard. And I came in one day, to my office, and I had my bedding all set up, and somebody had turned down my sleeping bag and put a mint on my pillow and left a little note that said, "Complimentary turn down service." It was crazy, crazy days.
And what Deep Impact was expected to do sounded a little crazy too. What's been described as hitting a bullet with a bullet. After the impactor is released, its onboard navigation system has to visually find the comet in order to execute 3 targeting maneuvers. 3 chances of zeroing in on the comet.
The impactor, once we release it, has an auto-nav system like we introduced with Deep Space One, and it locks onto the comet and tries to make sure that it's going to hit it. And it makes that first correction based on information from a long ways away. And so each successive correction as we get closer is going to be better and smarter. And so there wasn't a lot of actual commanding going on. It was mostly we're watching the spacecraft to make sure nothing funny happens.
All of this is to occur on the 4th of July. The comet Temple 1, not to be outdone, has already been shooting off its own celestial fireworks. Comets are known to sometimes have sudden outbursts, releasing massive amounts of gas, ice, and dust that briefly increase their brightness. The concern is that if Temple 1 decides to flare up during the encounter, the impactor's auto-navigation system could become confused. Worst case, the impactor might miss the comet entirely. It's not what the team wants to happen on a national holiday.
Mission, impactor flight, all impactor spacecraft subsystems green at this time.
It is now the 4th of July. The time of impact is 90 minutes away.
We are turning to the burn attitude, target ID 6. Copy, thank you.
The first impactor trajectory maneuver, or ITM, is underway.
Impactor flight, impactor prop.
Flight prop.
We see TCM thruster firing with accumulated on times increasing.
Copy, thank you. Flight confirms your go to radiate. Roger, on my mark. 3, 2, 1, mark.
Catbed temps look as expected. The accumulated on time is about right as well. And we'll give you a more full report later.
Copy, thank you.
The comet is not yet done with its surprises.
What's the most difficult issue that's confronting the team right now then?
Right now it's the comet, which is why we're going there. It's presenting a very strange shape to us. We've been watching it all day as we get closer. We initially thought that this thing was something like a pickle. As we're getting closer, it looks like it's more like a banana. And the latest resolution that we have in the rotation that it's going is that we're looking at the end of it, and the end of it is basically triangular. So it all depends on what that comet does and what type of face it presents to us, and we have to solve for that. So that's the challenge.
And it appears that this has been quite a temperamental comet. Over the last couple of days, we've seen several outbursts from it.
Yes, that's true. We have seen the actual jet outburst that brighten it, so it's very exciting for the scientists.
And nerve-wracking for the engineers. And even worse, the results of the first impactor maneuver were not what was expected.
It was the biggest movement off the comet we have seen, period. Even more than any of the simulations.
And that knowledge raises the possibility that deep impact might miss the comet entirely.
And the chatter is starting up that everybody's really worried on whether we can correct for that and come back in again.
Flyby AutoNav. Go ahead. The AutoNav flyby beeline is 365.8 by 341.0 with a time of flight correction of less than 1 second at this point. Flyby AutoNav. Go ahead. I'd like to add to that beeline information by saying we're about 1 kilometer off from the ground nav solution.
I was an extra set of hands, so I was basically moving around when issues would come up. As it turned out, that first correction kind of took us off in the weeds a little bit. They're aware of it and worried about it, but they're also like, it's supposed to bring us back. It was hair-raising.
After ITM-2, we have 6.5 kilograms of fuel remaining, which equates to 31 meters per second.
Flyby thermal. Requesting offline for 2 minutes.
Gang, sitting next to me, he looks like a ghost because all the blood just drains out of him. And he says, Care, I need to go off net for a few minutes. He goes off net, then he comes back 5 minutes later, and he looks better. And, he kind of leans over to me and whispers to me saying, I just threw up. Because he was so sick from how big the ITM was, and he wasn't sure whether we'd come back in again or not. We can't do anything about it. All we can do is trust the work that we did.
Go ahead, ACS.
We've seen the comet in all 3 cameras. We've seen it in the impacting camera, the 2 cameras on board the flyby spacecraft as well.
Providing live commentary during the event is Don Yeomans. Yeomans is blissfully unaware of the concerns over trajectory maneuvers, but he has his own reasons for being anxious.
They needed some stooge to get out there and talk to the
media. Either it was a smashing success or a horrendous failure. And so I was just worried sick that I would get this question after the fact that, Dr. Owens, NASA has spent $240 million on this deep impact mission, and you guys missed?
So this is our best image to date. It's only going to get better, much, much better. Now it looks bright, but it's actually a very jet black object that is being overexposed to show the light. It's sort of rotating around an axis that is more or less up and down. And so you're looking at the small end of the pickle here. It's a 9-mile pickle, mind you.
Impact flight, we've begun ITM-3. Impact flight, impact prop. We also see TCM firing for ITM-3. Copy.
The last of the 3 thruster burns is underway. Nothing more can be done.
Mission, this is flyby Pulpitech. Go. Reporting on our last enabled state change for flyby, final imaging before shield mode. We have a disable of all ADCS performance. Basically, we're left with what keeps the hardware talking. ADCS, you're on your own. Copy.
There are some of the images coming down from the spacecraft.
Oh, my, look at that. Looks like we've got...
No longer a pickle, more of an eggplant.
Yeah, now we're moving from the pickle to the eggplant here, and it looks like we have some clear surface features over there on the right. A dark depression, perhaps?
Look at the jets. Look at all the jets. Yes.
I have a little voice in my ear that tells me that we can put up the impact camera image in our monitor right now.
Okay. This is the impactor image, the spot where we're headed for impact. And the spacecraft's doing remarkably well for something that's about to vaporize. It's getting closer. We may be getting some serious dust hits. Our brave little spacecraft is in a very hostile environment here. We're going not only faster than a speeding bullet, we're going about 10 times faster than a speeding bullet. And that puts Superman to shame. We're expecting to lose the spacecraft any minute here. But it's doing one heck of a job just before checking out.
Flight, this is Telecon. We have lost the block. Copy that.
Tadi lebar mana tu top ada. Belum kayak kan pada top plan big plan ni. Ayo ni kan ni banyak tu banyak sekarang kan.
We got a confirmation.
The mothership, flying underneath the comet, recorded the aftermath. The impact was far more dramatic than expected, generating a brilliant flash of light and an immense fluffy cloud of ice, dust, and gas. That the comet's surface was so extremely fine, weaker than powdered snow, was a major surprise. This was